All right, let's get started on our next hazard analysis, and this is using a military surplus rangefinder. This is pretty common for universities to pick up surplus military hardware, and that is the case in this analysis. This is a piece of hardware we actually found at a university, and like I said, it's pretty common for to pick up surplus military hardware because it's cheap. It's inexpensive, does the job. Now, what these guys are doing, what they were doing, is that they were taking this piece of hardware, this rangefinder, and using it for some field tests. So let's load up record number 11. We highlight it, add-ins, easy has PDB, menu, load parameters from PDB record, and we have our result. Now we go through and we'll notice all the parameters that we've loaded in. We come over here and we say, wait a minute, where did you get 16.93 millimeter diameter beam? Okay. First, let me say that we chose 1.1 as this is a conservative value for m squared. We know this beam is a theoretically perfect beam, m squared of 1, but we do know that 1.1 is a conservative approach, yet the laser should be somewhere between 1.1 and about 1.3. So we chose a conservative value of 1.1. But how do we come up with this diameter? Well, it turns out from the previous slide you learned that if you clip a beam's power by 1%, okay, so that a total power of 99% is passing through the limiting aperture, you remove 17% of power from the center of the beam. It turns out it's the center of the beam that we're actually concerned with in the analysis. From previous work, we determined that this 99% criteria gives us the biggest beam, which gives us the lowest divergence we can have, and still keep enough power in the beam that this makes this the most conservative approach for using a beam at a great distance. So what we want to do for any limiting aperture we have, we want to use the 99% criteria. Now, what size, if I have an output aperture of 25.4 millimeters or 1 inch, what size should the beam be to pass 99% of the power? It turns out what we're going to do is look at a book from Anthony Sigmund called Lasers. It's one of the holy books of lasers. And Anthony Sigmund tells us that if you have an aperture diameter that is equal to 3 times the waist radius of the beam, that will give you about a 99% transmission. All right, so if we change waist radius to diameter, that's d over 2 for the beam diameter. That means 1.5 times the beam diameter is what we should set the aperture diameter to pass 99% of the beam. Well, in this case, we were given the diameter of the output aperture. Let's calculate the beam diameter by dividing the output aperture by 1.5. Let's get our calculator. And 25.4 divided by 1.5 equals, of course, 16.93 millimeters. That's how we establish that beam diameter. So now that we've done that, and with our m squared of 1.1, the software calculates the divergence at roughly 0.09 milliradians. That's super small, really small. That makes our NOHD really big, 22 kilometers. Okay, now since this is being used outdoors, wouldn't it make sense to use some atmospheric attenuation? Well, what kind of atmospheric attenuation should we put down here? Let's go to our user's guide. User's guide, remember, is found in your folder, right there, user's guide. And I'll even show you, let me go back up to the index. Here's the table of contents. Come down to Appendix B, atmospheric attenuation. Appendix B, atmospheric attenuation. Click that. It takes us to a graph. Now, we see that we used 6 times 10 to the minus 7. So that's right here for about a 1 micron wavelength around in here. 1.064 microns, 1064 nanometers. So it's what we're saying is it's between an exceptionally clear and a very clear day, somewhere in that. If you leave 0 in atmospheric attenuation, the system is working in a vacuum. So let's put 6e minus 7, and we'll see that the NOHD drops from 22 kilometers to 14 kilometers. So yeah, it's like a big filter. If you put in a hazier day, 6e to the minus 6, it drops even more haze in the day. Let's set this back to 0, 22 kilometer NOHD. Let's look what happens when we go to optically aided viewing. What we're doing here is saying, well, what if somebody's downrange using a standard pair of binoculars, 50 millimeter aperture, turns around and looks at this beam? So we click this on, we say yes. Oh, it goes to 132 kilometers. It's huge. Why? Because the limiting aperture, which you have just defined by flipping optically aided viewing to yes, is 50 millimeters. We have a 50 millimeter aperture collecting the power and then putting that through the 7 millimeter aperture of our eye. Notice also that the power transmitted through here is only 70%. That's because this is a standard for, this is a default for the ANSI standard for an infrared wavelength going through visible optics. You'll transmit about 70%. Okay? So this is what happens with optically aided viewing and atmospheric attenuation. You can see how they affect the NOHD. So that's about it for this one. We'll move on to the next one.